So welcome to our capstone presentation. The title of our presentation is Low-Level EMG Biosignal Acquisition, and we're working with Pison technology. These are our technical directors with Pison Technology, Jonathan Eagle and Tanya Wang. Tanya is a graduate of URI Engineering, class of 2013. I'm Hannah Morrissey. My major is electrical engineering, and my partner in this project is Jaden St. Germain. His major is electrical engineering with a math minor.
So for company vision and overview, their mission statement says, our mission as a company began with helping patients navigate the world made smaller and more challenging by their disabilities. Working with the ALS community, we pioneered the use of electroneurography, or EMG, to translate data generated by the body's natural physiological electricity into machine interpretable events. So, but what is EMG technology? So Pison's patented EMG machine learning algorithms derive neural intent 30 milliseconds before muscle movement occurs. Electrodes on the back of a wristwatch or wearable detect neural signals from the body's natural physiological energy. Machine learning algorithms translate neural data into machine interpretable events in the watch, wearable smartphone, smart hub, or cloud. And as for the project motivation, this project's focus is on the neural interfaces that fixate on gesture recognition, translating data from the body's natural physiological electricity into interpretable results. We are also trying to collect the most accurate representative signals as possible while filtering out everything else that we don't need, like noise and like signals like that. A complex understanding of biosignals is imperative in obtaining these readings and being able to convert them into data.
The anticipated best outcome that we're working towards in this project is initially, it's a developed system that can filter out all ambient noise coming from wires, cell signals, etc., and can also pick up on our body's biosignals, which are a very low voltage. We're hoping this will be achieved with the help of the LT-SPICE simulation as well as testing on a physical circuit. So far, our key team accomplishments are set up the project management tool using Jira software. We've learned how to interpret data sheets and look for key values. We've constructed fully functional analog front-end circuit in LT-SPICE. We've simulated the AFE circuit in LT-SPICE. We've created the Bode plot of the circuit to find the frequency cutoff and determined what to use for the instrumentation amplifier. We've tested noise of the amplifier test board, and we've learned how to use the spectrum analyzer.
This is the Bode plot that this is the Bode plot of the circuit that we built in LT-SPICE. We can see here that the frequency cutoff is around 100 hertz, maybe a little after that. And as for the noise of the test boards, we just started testing this recently, but we started by grounding the input and we connected the spectrum analyzer to the output to read noise with a grounded input. And then we also repeated that for the pizza board as well, and both in series. On top of that, we also input a 20 millivolt peak to peak input into both the test board, the pizza board, and both in series. And we also found the noise of those, and we are comparing the results from each to see where the noise is coming from and try to narrow it down and try to like point to where the noise is coming from.
So the economic impact of Pison, it's an overall positive economic impact in the world. Pison recently was selected as a finalist for Fast Company's World Changing Ideas Award in 2022. Pison's patented gesture technologies deliver a hands-free and heads-up advantage to America's warfighters. The team at Pison thrive on solving the most compelling real-world problems, and they do this by pushing the boundaries of human-machine interface in a culture of openness, intelligence, and care. On this slide is the project block diagram. This is what we've been following throughout our project. We're focusing more on the left side, where you can see our analog front ends sends a signal through the instrumentation amplifier, which sends that signal to be filtered to the analog to digital converter, which again sends another signal through to another part of the circuit, which processes that signal.
So as for my technical contributions, I started out by I learned how to analyze component data sheets because I had never actually looked at them before, and some of them could be like a couple hundred pages. And so it was really important to learn how to interpret and like read through these technical data sheets and like look for the numbers that I need that are important. After that, I helped create task cards and put them in Jira software just to help us keep on track. After that, I helped build the fully functional analog front end in LT Spice. What went into that was component research and like familiarization, just getting familiar with all of the buffers, op amps, all the chips that we're working with, just like how they work like with each other and how we can implement them into LT Spice. Another thing that went into this was I defined a suitable instrument amplifier to actually put in the Spice model, because there weren't any like Spice didn't have any models where I could just easily import it. I had to go online and download a suitable instrument amplifier that fit the specs that Jonathan and Tanya wanted. Another thing I had to do was I had to obtain op amps and buffers because again, Spice didn't have the models, so I had to download them from websites online and then import them into the Spice model. After that, we simulated the functional circuit. We obtained like the Bode plot. We found the frequency cutoff. We were showing everything is working as it should. And then after that, I also familiarized myself with the physical boards, and we just recently started noise testing. All right, so this is my to-do for April 15th, 2022. Our top task right now is I have to familiarize myself with noise. I started off by watching a YouTube video recommended by Jonathan. That helped a lot, but it can't hurt to just continue to work with noise and just like understand everything that it's telling me. Next, I have to test noise using the spectrum analyzer set into volts. I have to test the 1128 board alone with grounded input. I have to test the pizza board alone, and then I have to test both in series. And I also have to make sure that I test different channels on the pizza board just to compare and see how different the channels like react to noise and see how different like the noise gets amplified through the amplifier circuit. And then after that, Jonathan and Tanya recommended swapping resistors and capacitors just to see how the results of this noise changes, or if it changes at all, because it's important to see how the components in the circuit like results in the changing noise. After that, I have to send TD's document report with findings to compare and seek out where the noise is coming from. And then after that, it's up to Jonathan and Tanya to inform us on our next tasks.
So some of my technical contributions during the first semester of this project have been studying and familiarizing myself with the Pison schematics that were sent to us. I've been using LT Spice to build the analog front end of the device, which involved component research and familiarization. We've simulated the functional circuit in LT Spice and obtained a Bode plot to find the frequency cutoff of the circuit. And I familiarized myself with the two Pison PCBs and started noise testing. That also included doing some small soldering to get those boards ready. And so for my upcoming tasks for the next semester are to continue with the noise testing and observing noise outputs, testing noise using the spectrum analyzer set to volts. I won't repeat what Jaden said, but we're going to be doing the testing of the different boards. We're going to provide our TTs a report of our findings on the noise comparison of the PCBs, and we're going to continue, of course, with future tasks to work towards our ABO.
So for future team accomplishments, we're going to continue with noise testing and observing noise outputs. We're going to test noise using the spectrum analyzers at the volts. We're going to provide our TDs with a report of our findings on the noise comparison of the PCBs. I've already shared with them in a Google Sheet where I've been inputting all of the values, and we're going to use that sheet and fill it. And so over time, you can compare all the numbers with all the different inputs and we get in all the different channels, and we can use that sheet to just compare all the results and see what we're looking for. But other than that, we're going to continue working towards the best outcome, and we'll go from there. And I would just like to say thank you to everyone we've been working with: Tanya Wing, Jonathan Eagle, Dr. Sunak, and Mike Smith. Thank you.
Thank you very much for all your guidance and your mentorship. It's meant a lot to both of us, and it's definitely given us the opportunity to learn so much.